want to describe how to use the MATLAB program for solving PDEs that I discussed in class today. So here's the program that I showed you. So basically, it looks like it's written in Greek, but it's all built around this command, PDE-PE, which if you go to the help desk on MATLAB, here's the help desk on MATLAB, it will show you what it is. It says here, solve initial boundary value problems for parabolic elliptic PDEs in one dimension. One dimension means one spatial dimension. If you sort of scroll down, it says that PDE-PE solves PDEs of the following form, and here's the form. It's this thing right here. And basically, if you look at this, if you set m equal to 0, then this is essentially a conservation law. So this is some constant times du dt is equal to d by dx of a flux plus some source term. So if you keep this form in mind and go back to the MATLAB code, you'll start to see what it means. So basically, the deal is you define your mesh in X. So linspace basically defines a mesh which goes from minus 20 to 20 and 200 steps. So if I were to take this and just type it into the window, right, then you see this is X. So X goes from, right, X goes from 0, from minus 20 to 20 and 200 steps. That's what linspace does. Then this defines the time steps at which you output. So we output 10 time steps. 10 time steps going between 0 and 20. This calls PDE-PE. And there are 3 different subroutines that are in this program that need to be initialized. So one is called PDE1 PDE. This specifies the PDE. So this specifies C is 1, F is du dx, and S is 0. So that's these things. C is 1, F is du dx, and S is 0. So that basically gives it the diffusion equation. Because if C is 1, then this is du dt, and this is the second derivative of u with respect to x, and there's no source. So that specifies the equation. Then PDE-XIC specifies the initial condition, so u0, and this is the crazy initial condition I specified in class. There's also the possibility of doing the Gaussian, which is this one. And then the last one specifies the boundary conditions, and for that, you have to look a little further down on this. And you see the boundary conditions are imposed at either x equals a or x equals b, the 2 boundaries, and they're of this form, p plus q times f is equal to 0, where f is the flux function here. And remember, in our equation, we define the flux as du dx. F is du dx. So, and there's a left p and a right p, and you have to write it like this. So the left p, pl, I've set equal to ul, which is basically setting u to be 0. pr is ur, which is setting u to be 0 on the right, which is u at x equals 20. And the q's are both 0, which basically means that the flux term doesn't influence it. And that's it. That's basically the code. And so if we now run it, which we can do by doing the following thing. So here, I just write that. So that will run it. I called it PDE MATLAB, and it outputs xt and the solution. Then it will run it. So let's see. Here we go. And if I type the size of the solution, see the solution is 10 by 200, the size of x. X is 200, and t, there are 10 time steps. So this tells each of the time steps, this sol gives us the solution. So if I were to plot, write the initial one, x of sol 1. So that's the initial condition, and I can plot it at the time, let's see, I can do it at the 5th time. Let's see. That's the solution at time 5, or I could just plot them all. There you go, plot them all. And there it is. That's the time evolution. And so you guys can change this however you want. You can basically play around with the equation by manipulating this. You can play around with the boundary conditions. And this is just a good way to check your code. You can play around with the domain that you're solving it on. So you can solve, instead of minus 20 to 20, you can do minus 2 to 2. So this would go from minus 2 to 2, and so on and so forth.